Example 7.7. This one's going to require some serious visualization skills and some geometry skills. This is like combining motion on a slope with circular motion. So you might have to spend some time looking at and redrawing the free body diagram that I'll draw in just a second. So here's the scenario. You have a car driving in a circular path, once again. This time, what's providing the centripetal force is the banking of the roadway. So there's a normal force from the road that has a component pointing toward the center of the circle. We've turned off friction, so imagine it's a very slippery road, but you can still turn if you bank the road, because there's going to be a component of the normal force that points toward the center of the circular path. So the centripetal force this time will be provided by a component of the normal force that points in the radial direction. Of course, in real life, usually there's friction as well, and so in a more complicated version of this problem, you would consider both friction and the banking, but we'll just do the banking part, and you can add friction in some other time. Okay, so if we're given the speed and the radius, how much banking angle is needed so that the car can actually stay in the circular path? Well, let's look at this view where the radial direction is like that. The center of the circle is over here. I'm going to draw a free body diagram. And I have several directions going on, and kind of two different coordinate systems at the same time. There's horizontal, vertical, and now here is the sloped road that the car is on, and I'll put the car on it. And then there's the perpendicular, or the normal, to that sloped road. Like that. Now, the radial direction toward the center of the circle is that way. And I'll label this as the y direction. And I don't know if I really want to label all the other directions on the axes. We don't really need to. Now we'll draw in the forces. There's only two forces happening. It's just gravity and the normal force. As always, gravity points straight down. So gravity is in the negative y direction. And as always, the normal force is normal or perpendicular to the surface, which is the road. So here's the normal force. And we are interested in expressing the normal force in terms of its components relative to the r direction and the y direction. So picture this triangle here. There's the r component of the normal force, and there's the y component of the normal force. There's our angle theta. There's a right angle. I know this geometry is complicated. But that means that the radial component of the normal force will be n times sine theta, because this is the part of the triangle opposite to theta. and the y component of the normal force is n cosine theta, because this side is adjacent to theta. Okay, there's our setup. We need to get the magnitude of n, because that's not given to us in the problem. We can do that by looking at Newton's second law in the y direction. The car is not accelerating in y, it's not moving vertically up and down, it's staying at the same height. So we have the y component of the normal force minus gravity equals 0, or n cosine theta equals gravity force, mg, which means that n is mg divided by cos theta. This setup is a little bit different from the slope problems we've done before. So in the past we've had normal force equals mg times cosine theta, but because of where the angles are here, we just did the geometry, and for this scenario, it's normal force is mg divided by cosine theta. Now we do Newton's second law in the radial direction. Our radial force is provided by that radial component of the normal force, and again we give it a minus sign according to our sign conventions, and this is v squared over r for centripetal acceleration with the minus sign. These two minus signs cancel, and we get n sine theta equals m v squared over r. I just substituted n sine theta for n r. And we have found the magnitude of n, so I'll substitute that in. Notice the m's cancel out, and remember from trigonometry class that sine over cosine is tangent. Okay, so finally we get this relationship that tangent theta is v squared over r g, or if you prefer, theta equals inverse tangent v squared over rg. This is actually kind of a similar expression to what we found in the previous example, where we were using friction to hold the car in a circle. Once again, we find that this depends on the speed and depends on the radius of the circle. It's more difficult to hold the car on a circular path the faster you go and the tighter the radius is. When v increases, you have to make this angle bigger and bigger. When r decreases, you have to make the angle bigger and bigger. So on a racetrack, I think the example was talking about, I don't know, Indy 500 or some Daytona, one of those car racetracks. On a racetrack, you make it possible for cars to race faster by introducing this banking angle, because now you have both that bank and the friction between the tires and the road to hold the car in place so that it can undergo a centripetal acceleration around the turns without skidding. Of course, in car racing, a lot of times you do see cars exceed the radial force that's holding them in that circular path, and they skid out and they crash.